Module 6, Section 10.3, Vectors and their Applications. First, let's look at some basic terminology. A scalar is a magnitude, for example, 45 pounds. A vector quantity is a magnitude that has direction, for example, 50 miles per hour in the east direction. So we see here our blue line is our vector, 10 pounds is our scalar magnitude, and the direction is 30 degrees above the horizontal. Our vectors are usually represented in boldface type or with an arrow over the letters. Here we see the boldface, and here we see the letters with the arrow over top. For our vector OP, the first letter represents the initial point, the second letter represents the terminal point. And we see here, if we label it the other way, then our vector is going in the opposite direction. Vector OP and vector PO are not the same vectors. They have the same magnitude, but in opposite direction. Two vectors are equal if and only if they both have the same magnitude and direction. Here we see that A and B are equal, C and D are equal, but E and F clearly are not. In order to find the sum of two vectors A and B, first we place the initial point of B at the terminal point of A. So we're adding A and B. Here we put the initial point of B at the terminal point of A. The vector with the same initial point as A here and the same terminal point as B here is our sum A plus B, as we see in red or pink here. We can also use the parallelogram rule, where we place the vectors so that their initial points coincide here. Then complete our parallelogram as we see in the figure, and the sum of A plus B is our diagonal of our parallelogram. Parallelograms can be used to show that vector B plus A is the same as vector A plus B, or that A plus B equals B plus A. So that indicates that vector addition is commutative. The vector sum A plus B is called the resultant of vectors A and B. For every vector V, there is a vector minus V that has the same magnitude as V but in opposite direction. Vector minus V is called the opposite of V. The sum of V and minus V has magnitude of 0 and is called the zero vector. As with real numbers, to subtract vector B from vector A, we find the vector sum of A plus minus B. The scalar product of a real number or scalar k and a vector u is the vector k times u, which has a magnitude absolute value of k times the magnitude of u. So here we see u. When we multiply it by 2, it simply doubles. When we multiply it by 3/2, we have 1.5 times our vector. Times 1/2, it cuts in half. And times -2, it's doubled and in the opposite direction. A vector with its initial point at the origin is called a position vector. A position vector u with endpoint AB is written as u equals these slanted parentheses here, AB, where A is called the horizontal component and B is called the vertical component of our vector u, sort of similar to x and y in an ordered pair in our coordinate plane system. And here we see our vector u with our endpoint AB, and A being the horizontal component, B being the vertical component. The positive angle, theta here, between the x-axis and a position vector is called the direction angle for our vector. So we're able to find the magnitude of our vector by using the Pythagorean theorem in our right triangle here and taking the square root of a squared plus b squared to give us the magnitude of the hypotenuse, which is our vector. The direction angle satisfies the tangent of theta, which is opposite over adjacent, or in this case B over A, assuming A is not 0. Now let's look at an example. We want to find the magnitude and direction for our vector 3, negative 2. Remember that the magnitude of our vector is the square root of a squared plus b squared, where a is first and b is our second value. So here we have the square root of 3 squared plus negative 2 squared, or the square root of 9 plus 4, which gives us a value square root of 13. Our direction angle is the tangent of theta is equal to b over a, or in this case negative 2/3. So theta is then the inverse tangent of negative 2/3. So I want to make sure that we're in degree mode, and we are. And we'll take the inverse tangent of negative 2/3, and we see that we get approximately negative 33.7 degrees as our direction angle. Vector u has a positive x component and a negative y component, placing u in quadrant 4. Adding 360 to get a value between 0 and 360 degrees, or our coterminal angle, we'll get a direction angle of 326.3 degrees. Now let's look at our graphing calculator. The calculator screen returns the magnitude and direction angle given the x and y component. And here we see our calculator screen, so let's pull up our calculator and see the steps that got us here. In order to find the magnitude and direction angle, we're going to use our apps key because we want to get into our angle menu. So we press second and apps, and then go down to number 5. That gives us our magnitude. All we have to enter is our vector components. So we have 3, negative 2, and hit enter. And we see, if we compare this to the square root of 13, that it is the same. And then to find our direction angle, we go back into our apps menu, or second apps, to do the angle. And we go to number 6 and enter our vector components, 3, negative 2, and hit enter. And we see that we get our angle negative 33.7 degrees. If you wanted it in radians, you would need to make sure that your mode was in radian mode. The horizontal and vertical components, respectively, of a vector u having magnitude absolute value u and direction angle of theta are given by a equals the magnitude of u times the cosine of our direction angle, and b equals the magnitude of u times the sine of our direction angle. For example, let's find the horizontal and vertical components of w in the following figure. We see that the magnitude of w is 25.0 and our direction angle is 41.7 degrees. So to find our horizontal component, we know that a is equal to the magnitude of w times the cosine of our angle. So we have 25.0 times the cosine of 41.7 degrees. So we want to take 25 times the cosine of 41.7, making sure we're in degree mode. And we see that we get a horizontal component of about 18.7. Our vertical component would be the magnitude of our vector times the sine of our direction angle. So we have 25.0 times the sine of 41.7 degrees. and we see that we get approximately 16.6 for our answer. Now we could also find these using our angle menu. We press second, apps, and to find our horizontal component we'll go down to number 7, and we want to type in our magnitude and our direction angle, and we see that we get our value of 18.7. To find the vertical component we go down to number 8 and again type in our magnitude and direction angle, and we see that here we get our value of 16.6. Now let's look at properties of parallelograms. First, a parallelogram is a quadrilateral whose opposite sides are parallel. 2. The opposite sides and opposite angles of a parallelogram are equal, and adjacent angles are supplementary, or they sum to 180 degrees. And 3. The diagonals of a parallelogram bisect each other, but do not necessarily bisect the angles. So let's look at finding the magnitude of a resultant. Two forces of 15 and 22 newtons act on a point in the plane. A newton is a unit of force that equals 0.225 pounds. If the angle between the forces is 100 degrees, find the magnitude of the resultant force. Here we see our picture depicting our two forces, 15 and 22. We put their initial points together and draw our parallelogram so that the diagonal is going to be the resultant force, and we know that the angle between them is 100 degrees, so we found the other angle here using the fact that adjacent angles in our parallelogram are supplementary, meaning they must sum to 180 degrees. So then also the opposite angles will be equal, so this angle is 80 degrees as well, and this one would also be 100 degrees. Now to find the magnitude of our resultant force, we're going to use the law of cosines in either triangle, so we'll use this one here. And we know that our opposite sides are equal, so we know that this is 15 and this other side will be 22. And we have our angle between them, so we're going to use the side angle side here. So we have that the magnitude of our resultant squared will be equal to the magnitude of one force squared plus the magnitude of the other one squared minus 2 times those two times the cosine of the angle between them, which is 80 degrees. So we have 15 squared plus 22 squared minus 2 times 15 times 22 times the cosine of 80, and we want to take the square root of that to get the magnitude of our resultant, and we see that we get approximately 24 newtons. Now let's look at operations that we can do with vectors. For any real numbers a, b, c, d, and k, we have the following. We can add our two vectors. We simply add the horizontal and vertical components. We can multiply by a scalar. We simply distribute it to both. If we have a vector and we want to take the opposite of it, then it simply takes the opposite of both values inside. And when we subtract the vectors, we're simply adding the first vector plus the opposite of the second. So let's do an example. Here we want to find first, in part A, we want to sum our two vectors, u plus v. So we have -2, 1, plus 4, 3. And our answer will be the sum of our horizontal components and then the sum of our vertical components. So here we get 2, 4. In part B, we want to multiply by the scalar -2. So we'll have -2 times our vector -2, 1, which simply means that we'll distribute -2 times each value. So we'll get a value for -2 as our vector. And for part C, we have 4 times our vector u minus 3 times our vector v. So that would be 4 times -2, 1, minus 3 times 4, 3. So then we'll have 4 times -2 minus 3 times 4, and then 4 times 1 minus 3 times 3. So that gives us -8 minus 12 and 4 minus 9, or in this case -20, -5. Now we can't do vector operations on our calculator. Doesn't matter what mode we're in, but when we want to input a vector, instead of using the parentheses, we'll use our squiggly bracket. So we'll press second in our parentheses. So for time's sake, I'll do example C. We have 4 times our vector u, which was -2, 1, minus 3 times our vector v, which was 4, 3, and we press enter, and we see that we get our vector answer of -20, -5. Let's look at the definition of a unit vector. A unit vector is a vector that has magnitude of 1. Two very useful unit vectors are defined as I, which is 1, 0, and j, which is 0, 1, and we see them graphed here on our coordinate plane. I and j forms for unit vectors have the following definition. If v is our vector with components a, b, then it can be written as a times our vector I plus b times our vector j. So for example, if we have that vector v is 2, 4, then it can be rewritten as 2i plus 4j. And vice versa, if we have a vector written as 5i plus 8j, it can be rewritten as 5, 8. The dot product of two vectors, u and v, where u is a, b, and v is c, d, is denoted by u dot v and given as a times c plus b times d. In this example, we want to find the dot product of the following. So here we'll take 2 times 4 plus 3 times -1. So we'll have 8 plus -3, or 5. Notice that our dot product is no longer a vector. The dot product will be a scalar quantity. Now in part B, we're going to rewrite our vectors here. This is 6, 4 times -2, 3, which will be 6 times -2 plus 4 times 3, or -12 plus 12, so we get a value of 0. Notice that our dot product can be positive, 0, or negative. Now let's examine the following properties of our dot product, you'll notice that a lot of what's true with normal addition and subtraction of numbers is the same with our vectors. We can do the dot product in either direction. We can distribute the dot product here in B and C. We can change the order of multiplication with our dot product. The dot product with the zero vector is a zero vector. And when we do the dot product of the vector times itself, we simply get the magnitude squared. For a geometric interpretation of the dot product, if theta is the angle between the two non-zero vectors u and v, and theta is between 0 and 180 degrees, then u dot v is the magnitude of u times the magnitude of v times the cosine of theta, or the cosine of theta is equal to u dot v over the magnitude of u times the magnitude of v. In this example, we want to find the angle between the two vectors u and v. So remember that we have the cosine of theta is equal to u dot v over the magnitude of u times the magnitude of v. So u dot v will be 34.21, and the magnitude of u is the magnitude of 34 times the magnitude of v, which is 21. So in our numerator, we have 3 times 2 plus 4 times 1. In our denominator, the magnitude, remember, is the square root of our first component, our horizontal component, squared, plus our vertical component squared. We're multiplying that by the magnitude of v, so we have in our numerator 6 plus 4 over the square root of 9 plus 16 times the square root of 4 plus 1. So we have 10 over the square root of 25 times the square root of 5, which is 10 over 5 times the square root of 5. And that reduces down to 2 over the square root of 5. So we have that the cosine of theta is equal to 2 over the square root of 5, or that theta is equal to the cosine inverse of 2 over square root of 5. So we have the cosine inverse of 2 divided by the square root of 5. And we see that our angle in degrees is approximately 26.57 degrees. Now, we could have also done some of this on the calculator at the same time. We can do the cosine inverse of, we would have to find our dot product first, and we'll take 10 divided by, then in the denominator we want the magnitude of u, so we do second apps, and we do 5 with 3 comma 4 times the magnitude of v, so we do second apps 5 of 2 comma 1, and we see that then we get our value, our answer as well. Take note that if a dot b is 0, then the cosine of theta would be 0, and theta would then be 90 degrees. Thus, a and b would be perpendicular, or what we call orthogonal vectors. So we want to take note of that definition. For vectors to be orthogonal, their dot product is 0. Now let's do an application problem. A force of 176 pounds makes an angle of 78 degrees 50 minutes with a second force, as we see here. The resultant of the two forces makes an angle of 41 degrees 10 minutes with the first force. We want to find the magnitude of the second force and of the resultant. So we'll make our parallelogram here. Now, remembering that our adjacent angles are supplementary or add up to 180 degrees, we can simply take 180 degrees minus 78 degrees 50 minutes to get our angle here, which is 101 degrees 10 minutes. Then we can find our angle here, which would be 78 degrees 50 minutes minus 41 degrees 10 minutes, and we see that this angle would be 37 degrees 40 minutes. And this angle will be identical to our opposite angle in our parallelogram here, so we know that this is then also 37 degrees 40 minutes. Our second force here is identical to our value of our parallelogram here, since opposite sides are equal. So we'll call our second force x. And let's use the law of sines then in our triangle here to find the value of our second force and our resultant. So here we have x over the sine of the angle opposite it, which is 41 degrees 10 minutes, is equal to 176 over the angle opposite it, or sine of the angle opposite it, which is 37 degrees 40 minutes. So we'll multiply both sides by our sine of 41 degrees 10 minutes, to get our value for x. So we have 176 divided by the sine of 37 degrees 40 minutes times the sine of 41 degrees 10 minutes, and we get a value of approximately 189.59 or 190 pounds. Now let's do the same and find the value of our resultant, which we'll call capital R. So R over the sine of the angle opposite it, which is 101 degrees 10 minutes, is equal to our ratio from our previous part, which was 176 over the sine of 37 degrees 40 minutes. And we'll do the same. We'll multiply both sides by the sine of our denominator here. So R will then be 176 divided by the sine of 37 degrees 40 minutes times the sine of 101 degrees 10 minutes. So we get a value of about 282.57 or about 283 pounds.